Hi, today in Applied Calculus we're going to learn about the chain rule. So this will be the last of our derivative chants. Aren't you excited? All right, so the difference here is going to be that we don't just have x squared or something like that, but we have a quantity squared. So if we thought we could use the power rule on a problem like this 1 plus x cubed all raised to the second, then we know that we do something with bringing down the power. And we usually just rewrite x, so wouldn't we just rewrite whatever is in the power there? And then we know that we subtract 1 from our power. So the question is that right? And we know how to take the derivative of this by just distributing, by foiling, and then using the power rule, so we can find out. So if we FOIL this, we need to literally square it and be careful with that. And so this would be our original function, 1 plus 2x cubed plus x to the 6th, and we know how to take that derivative with the power rule. So when we go term by term and take the derivative with the power rule, we get this. And then all I've done is some cleaning up to make it look as close to what we were thinking might be right as possible. And so as I factored out the 6x squared and broke that down to see the 2, the piece that is different here is that 3x squared. And so this is not right. All right, so make sure you put a big X through that. But down here is what is right. And what we want to notice is the difference is this 3x squared. Well, where does that 3x squared come from? It happens to be the derivative of that inside function, 1 plus x cubed. So that's going to be our first case of the chain rule, a specific case. So we saw that the regular power rule did not work, but we need something called the general or extended power rule, just depending on which book you read. And so if we have a function raised to a power, instead of just x raised to a power, but something more complicated, we will still bring down the power, we will leave the inside alone, and then subtract 1 from the power. But the new part, and it's for this entire section, is that we need to multiply by the derivative of the inside. So this entire time you're doing this homework, that's the new thing. That's where your focus is, times the derivative of the inside function. So as an example, if I had the function x squared plus 5 all raised to the third, then to take the derivative with this general power rule, I'm going to bring down the power in front as the coefficient being multiplied, just like we do with the regular power rule. Leave the inside alone, subtract 1 from the power, and then I need to take the derivative of the inside. And so then, just like with our product and quotient rules, we go back and take the derivative of that inside. So we get 2x there. And so you might see someone combine the 2x and the 3 and say this is 6x, and then times the x squared plus 5 all squared. But in general, you're going to see I don't have you do a lot of cleaning up. And you can type things like this into MyMathLab, even if they show it in a more cleaned up form when you missed it. It doesn't mean that's why you missed it. So I won't have you do too much simplifying now that things are getting more complicated, because I want to know if you know the rules, not take all the extra time on the algebra at the end. So that's our general power rule. All right, so why is this here then? This is not a function raised to a power, or is it? Right? So if I see something with a square root, I need to rewrite it first, remembering that a square root is actually a power, right? A 1/2 power. So any kind of root, I need to first rewrite it, then I will take the derivative. So make sure you do that rewriting first. So now I'll write y prime because I'm taking the derivative. I bring down the power, leave the inside alone, subtract 1 from the power, and then multiply by the derivative of the inside. I can't stop here because I still need to evaluate that. So I'll just come back and do that. And be careful, a lot of times students don't notice that negative, that minus, means that the derivative of the inside would be 0 minus 2x, or in other words, negative 2x. And so you know, we could rewrite it to clean it up, but we are done taking derivatives at this point. If we were going to clean it up, this negative 2x does live in the numerator. This 2 was already in the denominator, so maybe you noticed something. And then this negative power means that the quantity 1 minus x squared should be in the bottom. And the 1/2 aspect of that means it should be under a square root. So I could have gone ahead and canceled these 2's back in the previous step, but otherwise I'm there. So it would be negative x over the square root of 1 minus x squared if I did clean it up. But at this point, I am done taking derivatives. So often my directions will say, take all necessary derivatives, but do not simplify. That means you can't stop here because there's still a derivative to be taken, but that you don't necessarily have to keep going after that. All right, let's look at one more. So again, I thought this was called the power rule. How can you rewrite that as a power, right? So I need to rewrite this to be something to a power. Well, if this whole quantity lives in the denominator, I can rewrite it to the negative 1 power. Now I can use this rule. So if you think about it, you would have previously had to use the quotient rule. And that's fine, but it's kind of a lot of extra work given that when you get to the derivative of the top, you're going to have a big fat 0 in there. So if you just see a constant over a function of x, this will be more efficient, but either way is fine. So now I am going to take the derivative, and I'm looking at this form. So I'm going to bring down my power of negative 1, leave the inside alone, subtract 1 from that power, and then multiply by the derivative of the inside. Well, what is that? We go term by term. 3x squared plus 4. So you can see that in the last examples, I was taking that extra step of saying times d dx of the inside and then coming back and doing it. But then as you get more and more under your belt, you might just go straight to here, and that's fine as well. So I wanted to show you what that would look like, to just go ahead and do the answer. So if we were cleaning this up, the negative and this derivative of the inside live in the numerator. This negative 2 power means that that inside should be in the denominator, and once it is, the power is positive. All right, so a couple more, just picking up the level a little bit, and you can expect to have something like this one or the next one on your test. So what we need to notice here is that this is not just the chain rule or extended power rule, that there's something else going on. So if you read this to someone over the phone, it would be the quantity 3x minus 3 all to the 5th times the quantity 1 minus x to the 4th all cubed. And so this is actually first and foremost a product rule problem. That's right, you can have both in one problem. And then it just so happens when you get to the derivative of the first or the derivative of the second that needs this extended power rule or general power rule. All right, so if we go to do that, our very first step is to write the product rule, and you've got to be saying your chant to do that. So there's a clear first in the big parentheses and second in the second big parentheses as we say our chant. So we have the first times I need to take the derivative of the second plus the second times I need to take the derivative of the first. Okay? So now we need to go back and do those little derivatives before we are done. If there isn't a d dx, then you just copy, literally, 3x minus 3 to the 5th, but here there is a d dx, so I need to actually take its derivative. So hide everything else and just take a deep breath. At this moment, all I'm asking you to do is to take the derivative of this. We just did 3 of them. So just because the problem is long, don't let that overwhelm you. Right here, put blinders on yourself. This is the only thing you're doing right now, and you need to bring down the power, leave the inside alone, subtract 1 from the power, and multiply by the derivative of the inside, which, be careful, is 0 minus 4x cubed, and so it's negative 4x cubed. And then we have plus, so we write a plus. We have 1 minus x to the 4th cubed, so we write that. And now at this moment, all I'm asking you to do is just this power rule. So do one thing at a time. Right now, I'm looking at this. I bring down the power, leave the inside alone, subtract 1 from the power, and multiply by the derivative of the inside. This is a fine answer. In fact, it's easier for me to grade than if you do clean it up. So you're done. All right, we're going to look at one more like that. And here you can see there's something having to do with quotient. But this time the order is a little bit different. So this time, the first thing that's happening is that there's an inside and an outside function. So this is first an extended or general power rule problem. And then when we do, well, let's get there. So we're going to bring down the power, leave the inside alone, subtract 1 from the power, and now when I get to the derivative of the inside, it just so happens that I'm going to need the quotient rule. So we will need to be careful not only about what rules are needed, because it could be multiple, but also the order that they're needed in. So I just rewrite anything that does not have a ddx, which is why you being consistent and correct with your notation is so important. And now, at this moment, just because it's in a bigger problem doesn't matter. All I'm asking you to do is the quotient rule, and you should have that chant down for sure by now. So we've got bottom times derivative of the top. Remember that it's a minus because that's important. The top times the derivative of the bottom all over the bottom squared. So again, there's definitely some cleanup we could do with multiple copies of x minus 3's floating around and all of that. But I want to know that you know the chain rule and the quotient rule, and this is a fine final answer for me. A little cleanup might make it easier to type into the computer in terms of homework, but you do not have to. You can type it like that. Okay, so that was specifically when the outside function was a power function. We are going to learn that the chain rule, which was actually the title of our section, applies to any composition of functions. So remember that this notation, it's a little circle. It's not an O, but you might have said fog and Goff, but it's f of g of x. It's in that order, f of g of x. And it does not mean f times g of x. That would be f of x times g of x. This is f of. So the function has to have an inside, and g of x is f's inside. So that's composition of functions. So it turns out that any time you are taking the derivative of something where there's an inside, right? So g here is the inside, and an outside function, that we can use this chain rule. So the chain rule is just a special case of the one that we've been doing for the last few minutes. So the chain rule is, our last chant, very important. Can't show up to a test on the chain rule if you can't chant the chain rule, right? The derivative of the outside function evaluated at the inside function, or I've been saying leave the inside alone, right? Times the derivative of the inside. And this is the key, right? This is what we've been talking about as being new today, is really remembering that piece. So we have the derivative of the outside function, leave the inside alone, then outside of that times the derivative of the inside function, okay? And so if you notice with the power function, it actually follows the same rule. It's just that our outside function was always the power function. So now you can just focus on the chain rule, and it encompasses everything. Okay, so there are two different, remember there's two different guys that discovered calculus at the same time, so there's two different notations floating around. There are two ways to think about this, and this is with the other notation, that dy dx notation. And so here, if you had y was f and its input was u, and then u was defined as some function of g, then notice that if you just replace u with g of x, it's the same thing we were just talking about, f of g of x. So in this notation, if we are doing the chain rule, this says if you're trying to take the derivative of y with respect to x, but that's way inside there, you have to take the derivative of y with respect to u, that first piece, and then the derivative of u with respect to x. So it turns out that this part is equivalent to what we've been doing, where we took the derivative of the outside and left the inside alone, and this part is equivalent to the derivative of the inside, because remember, the derivative of u with respect to x would be the derivative of this. So I'll post a video that shows this as a relationship between gears. It's like if you're trying to get from y to x, x turns the inside function and the inside function turns the outside function, and so that's why you need those two steps there. So some students, especially if they've learned it this way in the past, prefer this way. So at least one time I wanted to show you the other way of thinking about it. So if you were given a function x squared plus 2 all under a square root, you could decompose it this way and say, I'm going to call the inside u, and the outside is taking the square root of that. So you're just kind of breaking it down. And so if you did it this way, then the derivative of y with respect to x would be the derivative of y with respect to u. Well, this is u to the 1/2 if we rewrite it. So that's 1/2 u to the negative 1/2, just power rule. And then, so that's dy du. Then we would multiply by the derivative of u with respect to x. Well, the derivative of u is 2x plus 0, but 2x. Okay? But I can't have a mixtures of x's and u's, so what I need to do is go back and put the u in there. So if I put the u, so this was our du dx part, just so you could see where each piece came from. So if I go back and put the u in there, I'll have 1/2. U is really x squared plus 2 to the negative 1/2, and then times 2x. And there is some cleaning up that we could do, but we would have our derivative. So if you've seen that in the past, or if when you're watching other videos you prefer that way, then it's there. To go kind of back to how we've been doing this, because this one does happen to be one that applies to the extended power rule, since this is x squared plus 2 to the 1/2, we kind of have just been doing it through our chant all at the same time. So we said bring down the power, leave the inside alone, subtract 1 from the power, and then times the derivative of the inside. Whether you use a dot or parentheses doesn't matter. So either one is going to get you the same answer, and it's totally up to you which notation you start using, as long as you understand it and can do it well. Okay, so just to show you that we are going to keep revisiting that equation of the tangent line, and I said we're going to keep seeing it. It's just that what kind of function we're taking the derivative of will change. And so here I happen to need the chain rule to do this one. So remember, I always need a point. They were extra kind and already gave me the point, but remember, if I needed to find the y value, I simply would have done f of 2, which is 2 cubed minus 2 all squared. That's 8 minus 2 squared, or 6 squared, and that's where the 36 came from. So just this problem happened to give it to us, but remember, we can always find it. If you're only given an x, you would plug the x into the original to find the y and get that point if they hadn't given it to us. And then remember, we're going to use the derivative to get slope. All right, but we have to be careful because the derivative has to be evaluated at the point to be the slope. So when we go to find slope, we need the derivative. We bring down our power, leave the inside alone, subtract 1 from the power, and then multiply by the derivative of the inside. And so I don't really need the 1 power there because it is just 1, but you can leave it. And so now I can either clean it up a little bit, it doesn't matter. I guess I could even distribute, but I'm not going to. To get my slope, I need to do the derivative evaluated at 2. So I'm going to plug 2 into this. And so we have 24 times 6, and we end up getting 144 for our slope. So we have a slope and a point, and now we can write the equation of our line. So we have y minus 36 equals our slope 144 times x minus 2, and we can distribute. So y minus 36 equals 144x minus 288, and so 144x, and when we add, we get 252. Okay. So same process, use the original to get your y, use the derivative to get your slope, and then write the equation of the line. It's just that now your derivative might need the chain rule. All right, so we are going to learn about what this chain rule looks like for different kinds of functions. So the chain rule is the chain rule. The chant really works no matter what your inside and outside function are, but it is kind of nice to have examples of specific ones that we know will keep coming up. So when we apply the chain rule to e to the f of x, the outside function is e, and the inside function is f of x, its exponent. So that's a little bit different, but if you think about any programming, like if you were trying to type on a computer, you can't really get a second level when you're typing, and so computer languages use exp of x, and that would be e to the x. So it is its inside. The exponent is the inside when you're referring to an exponential function. And so when we say, okay, you take the derivative of the outside function. Well, remember, the derivative of e to the x was e to the x. It was itself. So you take the derivative of the outside function, that's itself, and then leave the inside alone. So it's still an f of x up there, so it's really, really itself. And then times the derivative of the inside. So when you take the derivative of an e function, you can either say to yourself the regular chain rule, or if it helps you, it ends up being itself times the derivative of the exponent. So let's do one. If I take this derivative, I will have the derivative of the outside, but I really did take it. It's just that the e is the coolest derivative ever, and it's itself. And I left the inside alone as well, so I really just copied and pasted the thing again. And then times the derivative of the inside is 12x cubed plus 5, because its inside is its exponent. So it's itself times the derivative of that exponent, because that is its inside. Okay, so what if we have ln of something more complicated than x? So now my outside function is ln, my inside function is whatever. In this case, some power rule stuff. So what does the chain rule look like here? I would take the derivative of the outside function. Well, I told you I hated the order of things because I did not want you to think that the derivative of every ln problem was 1 over x, because it's not. The derivative of an ln is 1 over its inside, but before our inside was just x. Now our inside is f of x, whatever our function is. So it's going to be the derivative of the outside ln is 1 over, leave the inside alone. So this one really kind of bothers people. The derivative of an ln does not have an ln in it. When we talk about leaving the inside alone, it's now down here, but it is, and then times the derivative of the inside. So it's 1 over the inside times the derivative of the inside. If you want to write it more compactly this way, that's fine. Just from a teaching standpoint, I always show it as 1 over the inside times the derivative of the inside to show that chain rule in action. And so if I do it for this problem, I'm taking the derivative the second I start saying these chants. And so it is y prime, and the derivative of an ln is 1 over its inside times back up top times the derivative of the inside. And so if you want to write it this way as 6x minus 7 over 3x squared minus 7x plus 2, or if you even want to go straight to that, that's perfectly fine, of course. So you should expect to have derivatives of both e's and ln's where you have the chain rule involved as well. And then lastly, one more thing that we learned back when we did exponentials and logs was what if it wasn't e as your base for exponentials or logs? So for any base a, remember the difference in our general derivative formula was that it was itself times ln of the base. And so that's going to be incorporated here as well. So the derivative, if we have a function inside a base a exponential, the derivative is itself times ln of the base. That's what we're already used to. And the new piece here is times the derivative of the inside. So itself times ln of the base times the derivative of the inside. So this is always an of, right? ln of the base. So if we look at this problem, 3 to the 2x squared minus 5x, the derivative is itself times ln of the base times the derivative of the inside. Okay? And that is me doing the derivative of the outside function, that 3 to raised to a power. That's here, leaving the inside alone or evaluating it at the inside. And then here is the times the derivative of the inside. So it really is the chain rule. I just want you to see what it looks like in some of the key scenarios that you'll keep seeing. And so our last one is what if it's not ln, what if it's not log base e, but rather log base any number, and you have an inside function that's more complicated than just an x. Well, that general formula was 1 over, at that time it was x, but now it's whatever is in the inside. So 1 over the inside, and the ln of the base went down there in the denominator, and then times the derivative of the inside. So that's back up top, okay? So we have 1 over the inside times ln of the base. All of that is still in the 1 over part. So that's where these parentheses are for. Then back up top times the derivative of the inside. So if I take this derivative, remember, it's kind of interesting. There's no, this goes away except that we end up with ln of the base, but we don't actually have a log written out anymore. So it's 1 over the inside. And I need to be careful and use lots of parentheses to be clear because this whole quantity gets multiplied by ln of the base. So times ln of the base still in the denominator. Then back up top, either you could have written it here instead of the 1, or I like to do it more step by step, the derivative of the inside. So 9x squared plus 2. So remember, with all of these that I was doing near the end here, I went ahead and did that derivative of the inside. If you still need to take the extra step of writing ddx of 2x squared minus 5x for this one and then coming back in a second step and rewriting and then doing the derivative, that is fine. And I think you might want to do that for a little while, and then you'll kind of wean yourself off of that and be able to jump more straight to the final answer. So again, I am not going to have you do a lot of cleanup at the end when we are doing these things that are already more complicated, incorporating multiple rules. And so now you are responsible for the power rule, the exponential rule, the log rule, the a exponential rule, the log base a rule, and then the product, quotient, and chain rules mixed in with those. All right? And then we're going to move on to applications of these derivatives as we continue.